Manish Gupta from Google DeepMind. So Dr. Manish Gupta is a senior director at Google DeepMind, where he leads AI research teams across India and Japan. He previously headed VideoCan and lead research centers from Xerox and IBM India, as well as subsystem software team from IBM's Blue Gene supercomputer. He holds a PhD from University of Illinois Urbana-Champaign UIUC and has authored 75 plus papers and 19 patents. So, Dr. Gupta is also a fellow of ACM and INAE and a distinguished alumni of IIT Delhi. So, with that, I like to welcome Dr. Manish Gupta on the stage. So, the stage is all yours.
Good morning. Thank you. So, it's a pleasure to me today for me to talk about the transformative power of AI and also some open challenges. So, I come from Google DeepMind, where our mission is to build AI responsibly to benefit humanity. And our team in Bangalore, particularly being in this part of the world where a lot of humanity resides, we take this humanity part quite seriously. So another very good, and it's great to see again forums like this, right, where we are now beginning to talk about how AI can be used to accelerate scientific discovery. And that's one of the most promising directions that we have seen of where AI can truly benefit humanity. And a very key kind of a milestone or a vivid kind of illustration, right, of the potential came from the Nobel Prize in Chemistry last year that went not to chemists, but to computer scientists, to AI researchers for their work on AlphaFold. And in fact, having worked on a machine called Blue Gene when I was at IBM Research, we worked on a supercomputer called Blue Gene, where one of the motivating applications was protein folding, understand the mechanisms of protein folding. In those days, protein folding was a grand challenge. It used to take an entire PhD, typically about 3 to 5 years of research, before you uncovered the structure of a single protein. And there used to be this contest held every 2 years, CASP contest, where all these models, software models, that were built to predict these protein structures, they would compete. And some newly discovered proteins whose structure was newly discovered, they would be posed as test problems. So in CASP 13, which was held in 2018, AlphaFold, which was again this time an AI-based model, it won the contest. It was placed number 1. And in the following CASP, which was CASP 14, which happened in 2020, the predictions of AlphaFold 2, which were shown here for some protein examples, the predictions are shown in blue, and the ground truth is shown in green. The predictions were so close to the ground truth that basically the community considered the problem as effectively solved. So no more CASP competitions being held anymore. And soon after that, the AlphaFold team, it made predicted structures of all 200 million proteins at that time known to humankind freely available. And today there are over 2 million, actually now I think the number has gone up to close to 3 million researchers across the world, including, I believe, over 150,000 researchers right here in India who are using some of these protein structures for a variety of problems. Of course, an obvious one is drug discovery, but you can even see things like designing enzymes to make plastics degradable, where people are using this to basically solve real-world problems. And then a follow-on, and so there has been work now on AlphaFold 3, which is now dealing not just with proteins, but pretty much all of the molecules. And most of these models are available for free for academic use. So you're welcome to make use of these. And another one where I don't have a slide is the co-scientist model, which in fact we've been in discussion with ISC as well as institutes like TIFR, ICTS, and CBS to make co-scientists available to under the Trusted Tester program to any of the researchers who may want to use it to advance their work. So more recently, there has been work done on Alpha Proteo, which is now looking at designing proteins. And in fact, my team in Bangalore is collaborating with the Alpha Proteo team because our team in Bangalore is doing some work on diffusion models, which has applicability to not just designing proteins, but also material science and so on. So these are some examples where, let's say you have a target protein, and this comes up in the context of, for instance, drug discovery, various therapeutics. Let's say you have a particular virus or a cancer cell which needs to be attacked, and you can now design proteins that will bind appropriately. And so more recently, there was work done by this Alpha Proteo team in looking at some of these important viruses, and then designing proteins to bind to them, and with some pretty good results in terms of being able to synthesize those proteins as well as good affinity in terms of binding. Now, while AlphaFold and these Alpha Proteo and so on, these are very kind of visible examples. These are not the only ones. There is a lot of work being done, be it material science, be it astronomy, be it things like weather, where AI is being used to accelerate, again, some of these simulations. So weather forecasting, today, we have some fairly strong, I remember growing up in India, there used to be weather forecasts used to be kind of almost the same every day, I remember. And always kind of, I even remember this R.K. Lakshman cartoon where there's bright sunshine and there's a guy kind of holding that umbrella for the rain, preparing for the rain, and somebody asks, "Who's this?" "Oh, that's the weather forecasting person. That's the meteorologist." Because the forecast used to be so bad, even when there were cyclones happening, causing widespread damage, you had that same generic forecast. Kahin kahin garaj ke saath cheete padenge. I remember in Hindi, these forecasts used to say. But now these forecasts have become very, very accurate. But they still are very computationally very expensive. So there's been work done on some of these model, GraphCast, GenCast, at Google DeepMind, where based on, again, because you have very high quality data available, these AI models are, in some sense, taking those shortcuts and providing even higher quality forecasts. So in fact, there was comparison done with ECMWF. This is the European Center for Medium Range Weather Forecasts. Their model, which is considered state of the art for medium range weather forecasting. We have seen these AI models from Google DeepMind outperforming that model and running much faster. It takes about 8 minutes on a single TPU chip compared to hours on a supercomputer. And today these models are being used to predict things like cyclones. And we are seeing fairly high accuracy in these models being able to show you the path of, let's say, a cyclone or a typhoon. And now, many of you may not realize, Google is becoming probably the world's largest weather forecasting agency as well. Because now when you do a Google search, I don't know about you, if I'm traveling to another city across the world, one of the first things I do is do a weather forecast check on Google to see what I should prepare for in terms of packing the right clothing and so on. And these weather forecasts on Google search are now beginning to get powered by Google's own models. So I'll come back to maybe sharing a bit more of the mainstream kind of directions that are being pursued in AI, starting with the recent history of AI and this new trend that we have seen in foundation models. And then talk about also its surprising success in areas like synthesis and creativity, and many of those techniques like diffusion models, which have been developed for creating images, beautiful images and videos, they are also being used now to synthesize new materials, synthesize new drugs, and so on. So it's very interesting to see very broad applicability of many of these models, technologies that are being developed more for the like mass market, but then with applications to science. Then I'll talk about inclusive AI, which is my favorite topic. How do we make all of these AI models work for everyone with that focus on humanity? Making sure these models don't just work for the Western world, but for everybody, especially billions of people who live in countries like India and this region, and then described some open challenges. So hopefully for this audience, I don't need to explain what is deep learning. So how many people know about deep learning? And how many people know at least some of the underlying mathematical foundations of how deep learning works, right? So I don't need to explain this slide. Often I need to explain to many audiences where people have heard the term deep learning, but they think deep learning is some black magic and kind of somehow just works. But I think this audience knows there are very strong mathematical foundations, including like this universal approximation theorem, which states that any computable function can be approximated by even a two-layer deep network. So while all of those things were known, things like universal approximation theorem, still the success of deep learning at a very broad range of applications was still very surprising in hindsight. It started with, in 2011, that breakthrough with ImageNet, where artificial neural networks, the community had given up on them for almost 2 decades. And then they made a comeback. And soon after that breakthrough, there were researchers who were able to train these networks end to end for a broad range of problems like speech recognition. So previously, machine learning researchers used to build these models combining acoustic model, language model, all cascaded together to build a model for a single language. And now you have, again, and soon after that ImageNet, that image classification breakthrough, there were researchers who showed that you could train a deep network end to end with lots of labeled data on audio signal and the text that was being spoken in that part of the speech, and these models started doing better at speech recognition. Similar thing happened with machine translation. After training these networks with millions of parallel sentence pairs, they found they were able to do now a much better job of translating, let's say, a sentence like "Hello, how are you?" to a sentence in French, and so on. So it looked quite good that, okay, deep learning was solving such a broad range of problems, but there were still 2 issues with this success. One of the issues was that typically for all of these problems, these networks required lots of labeled data. Often there were millions of data points that had to be annotated before deep learning worked well. The second problem was, for every problem, you had to train a new network from scratch. And this is not how we humans solve problems. Given a new problem, I kind of build upon all of my learning, years of experience, and experience with similar problems to solve that problem. So this is what got fixed by the new paradigm, which is foundation models, which is the paradigm that has become dominant today. And this was helped by this, again, one of the key breakthroughs, which was the transformer architecture that was presented at this NeurIPS conference, it just 8 years ago, it seems like ancient history because there's been such huge adoption of transformer architecture in the real world. And one of the first models to make use of the transformer architecture was this model called BERT that Google had released in 2018. And it was using the idea of self-supervision to deal with this problem of having to label all this data, right? So, I mean, if every problem you have to train a new network and train like and annotate millions of data points, it's not very practical, right, to be able to tackle all these problems using that approach. So the idea of self-supervision is where you use the labels inherent in the data itself. And so what BERT did was they looked at these freely available sources of text from sources like Wikipedia, digital books, masked out 15% of the words, and then started training a model to predict those words. So I don't know about you, it reminds me of this fill in the blanks exercise my English teacher would give me, actually any language teacher. I also learned in my school Tamil, in my school in Delhi. My Tamil teacher would also give us this exercise. And through this exercise, the teacher was testing this ability to understand kind of the language as well as reason about things from the context. So similar thing was happening with BERT. So when BERT was trained to predict those missing words, and to do that, it used the transformer architecture, right? So it would look at all these words in a context window. So to predict, for instance, that word Obama was born, to predict that word born, it is looking at all these surrounding words, Obama, 1961, Hawaii, and so on, doing these matrix multiplication operations through which, again, it is figuring out how much attention to pay to some of these words, and automatically figures out paying more attention, right, to some of these words like Obama, 1961, Hawaii, and predict the word born. And as BERT got good at predicting those missing words, it was now doing well at a very broad range of natural language processing problems, including things like sentiment analysis, question answering, text summarization, and so on. So fast forward to then a few years later, Google built a model called PaLM, which had 540 billion parameters. They did this very interesting experiment. They compared the performance of this one model PaLM on this benchmark called Big Bench with 58 different benchmarking tasks with the best known model for each of those 58 tasks. So remember, prior to this era, you had to train a new network for each problem. So this chart shows the relative performance of PaLM and the best model for each of those 58 tasks. So the charts, so the bars in that orangish color or whatever, reddish orangish color, they showed that the specialized model did better. The bars in gray show that PaLM did better. So you can see that for a vast majority of tasks, a single model is doing better than those specialized models that were built for those tasks. So it is this phenomena that led Stanford researchers to coin the term foundation models. That today, when you're solving a problem, instead of building a specialized model for that problem, you can start with these foundation models that provide an excellent starting point. And then either in a zero-shot manner or with some fine-tuning, few-shot manner, these models were doing quite well on those problems. And what the researchers saw was also that in addition to these NLP problems, it was even solving some very simple mathematical reasoning kind of problems, like what is shown here, that if you have this problem, John takes care of 10 dogs, each dog takes half an hour a day to walk, how many hours a week does he spend taking care of dogs? They saw that this model was able to answer this question, but only if it was also given similar kind of problems which required similar mathematical reasoning, and not just the answer, but also a step-by-step way of solving the problem. Again, reminds me of these instructions from our math teacher. Show me step-by-step how you're solving the problem. Don't just solve the problem. So if you showed the model step-by-step how to solve the problem, then there was this phenomena of chain of thought prompting, which was being extremely effective, and this phenomenon known as in-context learning, where these models are able to learn from similar examples. And note that this example, Sean has 5 toys. For Christmas, he got a toy each from mom and dad. It's not syntactically very similar to this. It's very different in terms of syntax. But the mathematical reasoning that this example uses is very similar to the mathematical reasoning here. So this is the power of in-context learning that these models started to show, that they were able to tackle some of these. And today, with this chain of thought prompting, these models are able to even achieve like gold medal level performance at International Math Olympiad. So achieving some very impressive feat. At the same time, I would also say that there's much more work that needs to be done to do reasoning in a like a well grounded manner. So this is still an open area of research, but approaches like chain of thought kind of reasoning itself has been taken to a very, very high level in these models that today, and today another thing that mathematicians are doing is they are coupling these language models with arithmetic solvers, and they are able to achieve some pretty impressive feats using that combination. The other interesting thing was this phenomena of foundation models wasn't just working for text, it was also working for images. So what our researchers saw was that for medical images, for instance, typically you used to have various companies building models, AI-based models, by using a lot of annotated data, right, just for that particular disease. Let's say you were building a model for, let's say, tuberculosis detection or breast cancer detection. You would only use those images, let's say mammography images, or only use those chest X-ray images and build that model. But what the researchers saw was that if you started to build these foundation models, even on unlabeled medical images, and then you fine-tuned them using some annotated examples, you started to get higher performing and more robust models. So which led, I was talking about Palm model. So Google built that model. We never launched any product. So that model was available in 2022. Google never launched any product based on Palm because of concerns about misuse of that model and problems like hallucination, biases, and so on that these models carried. And meanwhile, there was this company called OpenAI, which launched a model called ChatGPT, a product called ChatGPT in that same year. And despite all of the flaws of these models, hallucination, bias, and so on, they saw that millions of people were finding it very useful. So then Google also decided to get into the game and launched then Gemini model the following year. And what I'll do is I'll take you through some key aspects of Gemini. I don't mean this to be a marketing presentation, but would like to highlight a few of the technical capabilities that you can utilize. So one of the technical breakthroughs that Google launched with Gemini 1.5 in February of last year was this long context window. So another one that they showed was this ability for these models, even though they are known as large language models, for these models to handle multiple modalities: text, image, audio, video, all of the modalities. So a single model that handles all of these modalities. So now what that means is that when, let's say, you're responding, if you are interacting with the user using audio, you don't wait to convert that audio first into text and have the LLM process that text. You can directly process that input in audio modality and directly generate that response, let's say in audio, for instance. That's one. The other was this long context window capability, where if you remember this transformer, it operates on a context window, right, when it's doing that next token prediction. And this long context, which we initially announced 1 million token context window, what that meant was that this could, when making that next token prediction, right, which the model is doing, right, it is predicting the next token, roughly speaking, you can say the next word. It's the number of tokens it is looking at while making that prediction. So with 1 million tokens, you could, I mean, it's equivalent to almost like typically 600 to 700,000 words. So dozens of textbooks would fit within that, or something like 1 hour of video. So this was a particular demo which showed how it could process even a 45-minute video using this model. Okay, can I?
Experimental feature in our newest model, Gemini 1.5 Pro. We'll walk through a screen recording of example prompts using a 44-minute Buster Keaton film, which comes out to over 600,000 tokens. In Google AI Studio, we uploaded the video and asked, find the moment when a piece of paper is removed from the person's pocket and tell me some key information on it with the timecode. This screen capture is sped up, and this timer shows exactly how long it took to process each prompt. And keep in mind that processing times will vary. The model gave us this response, explaining that the piece of paper is a pawn ticket from Goldman & Company pawnbrokers with the date and cost. And it gave us this timecode 1201. When we pulled up that timecode, we found it was correct. The model had found the exact moment the piece of paper is removed from the person's pocket, and it extracted text accurately. Next, we gave it this drawing of a scene we were thinking of and asked, what is the timecode when this happens? This is an example of a multimodal prompt, where we combine text and image in our input. The model returned this timecode, 1534. We pulled that up and found that it was the correct scene. Like all generative models, responses vary and won't always be perfect. But notice how we didn't have to explain what was happening in the drawing. Simple drawings like this are a good way to test if the model can find something based on just a few abstract details, like it did here. These are just a couple examples.
Yeah. So
Gemini 2.0 enables new kinds of multimodal AI agents.
So next, let me talk about
Agents
Gemini
that can
2.0.
see and hear the world around you. Think, plan, remember, and take action. Gemini 2.0 is what enables Project Astra, our research prototype of a universal AI assistant. Using capabilities like multimodal memory and real-time information, it lets you understand your world live.
What can you tell me about this sculpture?
The sculpture you're seeing is called My World and Your World by Eva Rothschild, located in Lewis Cubitt Park in London.
What kind of themes does her work explore?
She creates abstract sculptures that invite viewers to interact with and interpret their surroundings in new ways.
Project Astra is multilingual, using native audio to seamlessly switch languages as you speak.
Est-ce que tu peux me dire quelque chose d'intéressant à propos de ces lanternes?
Bien sûr, je peux vous parler des lanternes. Les lanternes que vous voyez font partie de la porte d'entrée de Chinatown à Londres. நிச்சயமாக இது லண்டனில் உள்ள Chinatown நுழைவாயில்.
We're taking this to the next step with Project Mariner, with agents that can complete tasks on your behalf. You can ask it to do things like this that require multiple steps: doing research to look up the artist, then finding the painting, and then shopping for the right supplies. The agent uses the web to take action and find what you're looking for. It plans and reasons at each step, always staying in your control and completing your task. Gemini 2.0 enables agents that can be applied across domains. We're exploring agents that can explore virtual worlds, assisting you in video games.
Where do you recommend I attack from in the space?
Given the base layout, I'd recommend attacking from the bottom or south side. This direction allows you to target the town hall directly with your giants, while the wizards can handle the surrounding defenses.
Gemini 2.0 can reason about the physical world, understanding 3D spatial environments and objects. These capabilities are being applied to robotics, with agents that can assist you in your everyday physical environment. Learn more about how Gemini 2.0 is enabling the next generation of multimodal AI.
So I'll skip some of these in the interest of time. So more recently, we launched Gemini 3 last month, which again has really captured the leadership on a number of benchmarks on coding and a lot of these, in particular, very strong multimodal capabilities. So with these models, now a lot of what you would think of previously as science fiction is now becoming possible, right? So things like interacting with videos. So we have capabilities where now, as you bring those capabilities to even learning videos and so on, you can actually interact with those learning videos. It can help you answer various questions and so on. So I'll skip some of this in the interest of time. Let me just present very briefly this work on diffusion models, which has also become extremely powerful. It was originally motivated for many of these image generation problems. And the idea itself is inspired by the laws of thermodynamics, where what you do is you first convert this data into noise, and then you denoise. There's a denoising step where you convert this noise back into data in conformance with the data distribution, the probability distributions and so on that you have. So this has been used to create all these images. Similar kind of model, similar techniques are being used to likewise synthesize, let's say, molecules, synthesize different, let's say, proteins for drug design or new materials which would have certain properties. Already what we have seen is that these models are able to, given a text prompt, are able to generate very high quality images. These are all examples of images that have been generated by this Imagine 4 model. And also at generating video. So here's an example of a video which has been entirely AI generated.
This ocean, it's a force, a wild, untamed might. And she commands your awe with every breaking light.
So that digital actor, the sound, including the soundtrack of ocean waves in the background, the delivery of the dialogue in a very natural style, the movement of lips in sync with the audio delivery, all of this has been AI generated. So you can see that, again, day is not far, right, when you would have Hollywood, Bollywood using these models in a big way. And the way in which we are trying to get these models to be used is as assistants to people, not as replacements for human artists. I'll skip this slide, but this shows again some things, some work that we did with Rahul Mahadevan on helping him. Sorry? Sure, sorry, Shankar Mahadevan. Rahul Mahadevan is a researcher, in fact, an ISC graduate who works in my team. Sorry about that. So, am I out of time? 2-3 minutes. Okay, so I'll very briefly now share a little bit about how the work that we are doing to make all of these models truly inclusive. In particular, our team presented this benchmark called Indic GenBench at ACL conference last year, where we showed that there's a huge gap between the performance of all these impressive capabilities that I showed you in English versus most Indian languages. So we've been working on this model called Morni, where we are targeting not just the 22 scheduled languages, but each of the 125 odd languages in India, which has over 100,000, which has over 1 lakh speakers. And many of these languages are zero corpus languages, or let me say, were zero corpus languages because there was zero known digital data. This is where we have been working with ISC, with Art Park at ISC on Project Vani, on collecting speech data from different corners of India. In fact, I need to update this slide. I just got some updated numbers a few days ago. We have already, through this data that has been collected from close to 143 districts, uncovered now over 110 languages. And for many of these languages, like 35 of these languages, this is the first ever speech data, and this is the first known digital data for 22 of those languages. And all of this data is freely available to researchers, to practitioners. And in addition to Google, it was very heartening to see a number of startups. Like I saw some postings from SandLogic, Shunya Labs, which have built models using this data. We also figured out a way to compose models like Morni with a model like Gemini to be able to get the best of both worlds. And we have been able to produce a model Gemini. Since Gemini 2.0, we have been consistently showing the highest performance, highest quality on a whole bunch of Indian languages. And through this, we were able to add, the Translate team was able to, in one shot, add 110 new languages in one shot to Google Translate as a product, including 7 new Indian languages, so bringing the total to 28. Maybe I'll stop with this.
How Gemini can help.
Slide. This is, okay, maybe let me just stop here. Let me just, so one of the things we've been looking at is how can we enable, for instance, learning solutions. So I showed you the demo of Astra. We are looking at how can we enable a personalized tutor that can work with each child in their native language. So this is a demo of that capability currently in our lab.
And let's take a look at how Gemini can help.
नमस्ते.
क्या आप क्वेश्चन 3 सॉल्व करने में मेरी हेल्प कर सकते हैं?
हाँ, मैं समझती हूँ कि आप चाहते हैं कि मैं इस इक्वेशन 3x² + 5x - 2 = 0 में x का हल निकालूं. क्या आपने इसे ट्राई किया है और क्या आप मुझे इसके स्टेप्स दिखा सकते हैं?
हाँ, मैंने क्वाड्रेटिक फार्मूला यूज किया है. क्या ये ठीक है?
हाँ, ये सही तरीका है, पर आपने डिस्क्रिमिनेंट में एक छोटी सी गलती की है. आपको कोएफिशिएंट c के आगे एक माइनस साइन छोड़ दिया है. सही कोएफिशिएंट्स हैं a = 3, b = 5 और
so
c
I'll skip
=
this, but basically now the dream of personalized tutor for each child in their native language, now it looks very realizable. Of course, there is still a lot more work to be done, but these kinds of capabilities, and this isn't like, this is actual AI model. This isn't like some artificially generated demo. This is actually the AI model being able to work on those problems. Now, making it more robust and more generalizable, I think gives us that opportunity to provide personalized assistance to every learner. So with that, let me stop. There are a lot of other areas like agriculture, where again, we have created and made available freely a model that for the entire level of the entire nation, it identifies farm boundaries, identifies crops being grown and so on, to provide the low levels of an agri stack, and a lot of work on making these models more efficient. But let me, in the interest of time, just point out just a quick thing, that while I've talked a lot about the powerful capabilities, I would say there are a lot of challenges still that are open. So for the PhD students out here, I can say there are easily at least hundreds, if not thousands of PhDs to be done on tackling some of these open challenges that still remain, because we are in this very interesting era. On one hand, these models are becoming very, very powerful and being used by billions of people. On the other hand, there are still glaring weaknesses. So with that, let me conclude that AI is already here, impacting every industry, the world at large, and in particular impacting the field of scientific discovery, how we do scientific discovery. A lot of that is being made possible through these generative AI models, methodology through which we are building these foundation models. And it's truly, certainly for me as a researcher, it's been the most exciting time of my career, truly amazing time for us to be living in, where we can use our technology to make a real difference to the world, literally kind of help billions of people across the world through the work, technical work that we do. So with that, let me stop and thank you.
Thank you, Manish. Thank you for the wonderful discussion on the topics and sharing the ideas, how DeepMind has contributed, how your team has contributed. In fact, we have seen that, right, the innovation, especially in the scientific research and R&D innovation, is no longer associated only with academic institutions. Google has shown, and starting from the AlphaFold experiments and the prize, and whatever they are doing right now is also like phenomenal work. I know that there will be multiple questions again. In the interest of time, let me take 2 questions, right? Maybe the first question here.
Hello, sir.
Backside.
Thank you again for this amazing
I will
talk.
come to you, yeah.
So we have seen in the recent days, foundation models are getting adapted for every downstream task under the sun. And for adapting a model like that, we use strategies like RLHF, system prompting, and in-context learning. So what are the new paradigm shifts this Google DeepMind is exploring in terms of adapting these models to complex tasks, more complex tasks?
Yeah, so while there is a lot of work being done, for instance, in reinforcement learning, right, to ultimately make these models more powerful, we're also doing a lot of research on, are there other ways in which you can make these models reason better? So one particular paradigm which we are focused a lot on is building agents that are continuously learning. Because today these models have certain capabilities, but there are problems that they cannot solve. So is there an agent that can automatically identify which are the hard problems that this model is unable to solve, and come up with a plan to improve the model to be able to solve that problem, which includes even figuring out the data that it needs, even figuring out how to kind of enhance the model. So there is kind of this whole, because once you can get such a continuous loop going, you can have the model continuing to refine and improve itself. So that's kind of one example of a body of work which is being done at not just Google DeepMind, there are other researchers. In fact, there was a keynote talk at NeurIPS by the Turing Award winner, Richard Sutton, on that topic. So that's one example. There are also, our teams are right now also doing a lot of work on making these thinking models more efficient, because today these are quite expensive, but I've certainly been encouraging my teams, as well as more broadly, we have efforts going on at DeepMind at looking at alternate ways in which these models could do reasoning. Because today, the reasoning, while in many cases it's very, very impressive, it's still very brittle, because these models often fail at some. Also, while on one hand they may solve a gold medal level math problem in Math Olympiad, on the other hand, they may fail at a simple problem like maybe some multiplication of 2 numbers. They may fail at that. So how do you make these models more robust, be able to reason more effectively using, because we humans, right, we are able to use abstractions, and we are able to kind of learn from all of the wonderful work that the Einsteins and Ramanujans and so on, right, of the world have done before us, where they are able to learn new things, they are able to encode them, right, in certain ways, in certain abstractions, and we are able to start from, like, as we do some formal learning, we are able to build upon those abstractions. today these models aren't really able to do that very effectively. So that's another direction.
Okay, thank you. She's having the second question.
Thank you for the wonderful talk. I would like to, what do you think is the biggest limitation of Gemini right now? And what is the future that you see for Gemini for maybe for next 5 years? Is it, I see all the list, but what is the biggest one that you
so
see?
biggest limitation in my view would be, I would say, reasoning and planning. This is where we are really both, I mentioned the agentic work that is being done as well as kind of new ways of doing reasoning.
Yeah.
Efficiency, I mean, if you look at human brain, right? Human brain does it with about estimated 20 watts in power consumption, whereas these models are consuming so many like kilowatts or megawatts and so on. Today, you are talking about new nuclear reactors being constructed just to kind of power these data centers across the world. So I believe we need to make huge improvements in pretty much across the board in energy efficiency. Of course, there are things like factuality and so on that I didn't talk about today.
Thank you.
Thank you. I know that there are many questions, but in the interest of time, right? So definitely you can post the question there, right? And we will try to answer it. So once again, thanks the speaker for the wonderful talk and given insight, and just a small token of appreciation.